Now let us look at what the vehicle requires, like in order to drive it and meet some vehicle performance requirements. As we talked about initially, when we want to design a powertrain, we want the powertrain to satisfy some vehicle performance requirements such as maximum speed, maximum acceleration, gradeability, right, fuel economy, range and so on. So now the question arises, like how do we look at this from the vehicle's perspective, and then like try to match what the powertrain is giving with the expectations of the vehicle. So let us look at it from that perspective. So let us do an analysis with respect to what are all the forces acting on the vehicle that need to be overcome by the powertrain and drive the vehicle. So let me introduce a very simple free body diagram of the vehicle. Okay, so just to illustrate and discuss what are all the various forces acting on it. Okay, so let us consider this free body diagram. So what we have is that like we have a car moving up a grade. Okay, so the direction of motion is like this. So the grade angle is denoted by theta s. Okay, so that is the grade angle of the slope on which the car is moving. Okay, so let us say the acceleration of the car is some a, and this is the center of gravity of the car. So W is the weight of the car. So this we take it as m times g. M is the mass multiplied by acceleration due to gravity. Now we can see that I have marked essentially W by g times a, which is m times a. M times a is nothing but the inertia, right, inertia term which one needs to consider, and I have marked it in a direction opposite to that of the deceleration. Typically this is what is called as the D'Alembert's force, right. So if you recall basic dynamics, what we do in the D'Alembert's approach is that we introduce this inertia term at the vehicle center of gravity, and what we do is that like we convert this problem into an equivalent statics problem, so that like we can essentially sum all the forces acting along the direction of motion to be 0, and we could also take moments about any point, okay, and equate that. So that is the process we are going to follow. So let us say the point of contact at the front and the rear tire rod interface is denoted by A and B respectively, okay, and WF and WR indicate the normal load at the front and the rear respectively, okay. So WF and WR are the normal loads at the front and the rear respectively. So obviously WF plus WR should be equal to W, right. So that is the net weight. Of course we are essentially considering this as our we are considering more forces, okay, we are coming one by one. So this capital L is what is called as the wheelbase of the vehicle, okay. So that is the distance between the front wheel center and the rear wheel center of the vehicle, okay, and the center of gravity is taken to be at a distance of L1 from the front wheel center and L2 from the rear wheel center. So consequently L1 plus L2 will be equal to capital L, okay, and it is considered that this center of gravity is at a height h from the ground. Okay. So, the height of the center of gravity from the ground is h. Okay. Now, Ff and Fr are the tractive forces at the front and the tire rod interface respectively. Okay. Ff and Fr are the tractive forces. So, the tractive forces come from the powertrain. Okay. Of course, they are also very closely related to the tire rod interface conditions. Okay. We will discuss them later on. But if you have a, for example, a front wheel drive, Fr will be 0. If you have a rear wheel drive, Ff will be 0. So, depending on which wheels are driven by the powertrain, we have to consider the corresponding tractive force. If you have a 4 wheel drive, both Ff and Fr will be non-zero, okay, and so on. Okay. So, without loss of generality, I am indicating both Ff and Fr. Now, what is this Ra? Ra is the aerodynamic drag which has been lumped on the vehicle in this manner. Okay. So, as a vehicle moves, like we are going to have air flowing past it, over it, and so we are going to have this aerodynamic resistance, which essentially is quantified and lumped by this variable Ra. Okay. And typically this is taken as rho A CD AF VRL square. Okay. So, what is rho A? Rho A is the density of air, CD is the drag coefficient, AF is what is called as the frontal area of the vehicle, VRL is the relative speed between the vehicle and the local wind speed. Okay. So, that is how this aerodynamic drag is quantified. This aerodynamic drag is a result of what is called as pressure drag and viscous drag. Pressure drag is due to the normal component acting on the surface, right. Viscous drag is due to the formation of boundary layers as air travels upon the surface of the vehicle, right. So, both contribute to this aerodynamic drag, okay, and that is lumped for our analysis at this point denoted by this Ra, and the height of this aerodynamic drag from the ground is taken to be some h subscript A. Okay. So, that is the notation that we are following. Okay. We are lumping all the aerodynamic resistance forces as one quantity, right. Now, what is this Rd? Rd is what is called as drawbar pull. So, what is this drawbar pull? Suppose I hitch something to my vehicle, let us say a small trailer, right, to my vehicle, and I want to pull that trailer along with my vehicle. So, the trailer requires some force, right, to displace it. So, that is what is denoted by Rd, drawbar pull, and that is assumed to act at a height of h subscript d. Of course, if you do not hitch anything to the vehicle, drawbar pull is 0. Okay. So, without loss of generality, I am including the drawbar pull also. Then we have two more forces, what are called as rolling resistance forces at the front and the rear respectively. Okay. RRF and RRR. RRF and RRR are the so called rolling resistance forces. So, what is this rolling resistance force? The rolling resistance force comes about because the pneumatic tire, okay, has hysteresis loss, when it is rotating, okay. It sticks to the road surface and then slips, okay. And due to the deformation of the pneumatic tire and due to its viscoelastic nature, there is a hysteresis loss, and that gets realized as this so called rolling resistance. So what happens? So let us say I draw a very simple schematic. So this is the rotating tire, I am just exaggerating just to convey the concept. So let us say the tire is rotating counterclockwise, okay, and this is the tire rod contact patch or the contact area. So what happens is that due to this hysteresis laws, the normal stress distribution at this contact patch is asymmetric, okay, it is shifted in this manner. So if you take the resultant of this normal stress distribution of the tire rod contact patch, what will happen is that you will see that there is going to be an opposing resultant moment, right, because the normal stress distribution is asymmetric. So this moment is what is called as a rolling resistance moment, okay, which is denoted by M subscript R. When we want to essentially account for it, when we want to analyze the translation of the vehicle, translational motion of the vehicle, we introduce an equivalent force which is what is called as a rolling resistance force, okay, which is denoted by R subscript R. Okay. So R subscript R is the total rolling resistance force, which is the sum of this RRF and RRR. The additional subscript F and R denote front and rear respectively. And typically this R subscript R is taken as FR times W, okay. For first cut analysis, simple analysis, we assume that the rolling resistance force is directly proportional to the weight of the vehicle, okay, and this coefficient FR is what is called as a rolling resistance coefficient, okay. We shall consider it to be constant for our first cut analysis, and we shall express rolling resistance force as product of the rolling resistance coefficient and the weight of the vehicle, okay. So this is the background. So these are all the different forces, their physics and also the way they are expressed, okay. So we are going to use these in our calculations. So if we look at what are all the loads that act on the vehicle during traction, so these are some terms that we would encounter, so when we do this analysis. So what people mean by load on the vehicle are the resistive forces that the powertrain needs to overcome, right. So the loads or the resistive forces are inertia, because when we are accelerating, the inertial term becomes important, M times A, right. Then aerodynamic drag. Aerodynamic drag becomes very important, particularly when we are cruising at mid and high range speeds, okay. It may not be very significant at low speeds, of course it depends on the type of vehicle, right, but it becomes more critical when we are cruising at constant speeds and the speeds are in mid to high ranges, okay. So there aerodynamic drag plays an important role. Then we have rolling resistance, then we have grade resistance. What is grade resistance? Grade resistance is W sin theta s, right, because there is going to be a component of the weight along the grade, along the slope, right, which has to be overcome by the powertrain when the car is or when the vehicle is trying to go up the grade. So that is what is called grade resistance. Some people will put a plus or minus sign to it just to indicate that it is a resistance while going up, but it aids motion while coming down. So, the plus sign indicates that it is a resistance while the vehicle is going up, the minus sign indicates that it is aiding motion when the vehicle is coming down the grade, okay. And another load is what is called as drawbar pull, okay. So, these are typical loads that act on the vehicle. So, this is the setup, okay. So, now the process that we are going to follow is the following. We are first going to sum all the forces along the direction of motion, we are going to balance them, right. Then what we will do is that we will take moments about points A and B, so that we get expressions for WF and WR, okay. So, that is the analysis we are going to do. So, balancing forces along the direction of motion yields the following, right. So, we have m times A to be equal to FF plus FR minus aerodynamic drag, okay, RA, minus the grade resistance R subscript G, minus the drawbar pull, minus the rolling resistance at the front wheel and the rear wheel respectively, okay. So, these are all, we are just balancing the forces, alright, okay. So, typically in most analysis of road vehicles, you will find that like the mass of the vehicle is typically written as W by G, okay, and even the acceleration levels are normalized by G, okay. People will talk about acceleration or deceleration in terms of G units, okay. So, that is a convention. So, we will write m as W by G, okay. So, this F plus Fr is the net traction force F, okay, and this RRF plus RRR we will take it to be the net rolling resistance RR, okay. So, consequently what will we get? We would get the net of course RR, as we discussed earlier, we will take it as Fr times W also, right. So, using this above equation, we will get the net tractive force that is needed to overcome the loads will be W by G A plus aerodynamic drag plus the rolling resistance plus the grade resistance plus the drawbar, okay. So, this is one equation, okay. So, let us call it as some equation A, right. So, it is pretty intuitive, right. So, the net force, traction force that is provided by powertrain should overcome inertia. These are the 5 loads, right, inertia, aerodynamic drag, rolling resistance, grade resistance and drawbar pull, whatever we just wrote down, correct. So, that is what we need the powertrain to overcome. Now, what we do? We will take moments about point A. Let us do that exercise. So, now taking moments about point A yields. So, what do we get? So, if we take moment about point A, please note that there is a component of W cos theta s, right, which will provide a clockwise moment, and there are other forces which provide a counterclockwise moment, right. So, we are just going to balance out all these moments, right. So, if you look at it, when we take moments about point A, WR times L is going to be a counterclockwise torque, right. Do we have any other counterclockwise torque? due to any other force? When we take moments about point A, no, right, the torque due to all other forces are clockwise, right, because we are at point A, we are taking moments of all the forces about point A. Please note that the rolling resistance force and the traction force will not be having any moment, right, because they pass through that point, correct, the momentum is 0. So, we can immediately see that WR will have a counterclockwise torque, all the other forces we will get a clockwise torque. So, let us write them down. So, one torque is going to be W cos theta s times L1, right, that is the torque due to this force, right, this component. Then what do we have? We have a torque due to the other component, right, W sin theta s times h. Then we have a torque due to the inertia term W by G A times h. Then we have a torque due to the aerodynamic drag. Then we have a torque due to the drawbar, right. So, this implies that WR, which is the net load on the rear wheel, the normal force on the rear wheel, will be 1 by L W L1 cos theta s plus W by G A times h plus R A H A plus R D H D plus W sin theta s times h, right. This is another equation. Okay. So, let us call this as equation B. As it mentioned, some people will write for this, they will write plus or minus, because depending on whether the vehicle is climbing up the grade or down the grade. Okay. We are considering the case where the vehicle is climbing up the grade. Okay. So, similarly, if you take the moments about point B, I leave it to you as an exercise, taking moments about point B yields, finally, like if you simplify, you will get WF to be equal to 1 by L W L2 cos theta s minus W by G A H minus R A H A minus, oh, this should be R D H T, right, sorry, okay, R D H T minus W sin theta s h. Okay. So, this is what we will get for the other one. Please do this, like it is pretty straightforward, right. So, let us call this as some equation C. As I mentioned once again, some people you will see this expression as minus plus, okay, just to indicate climbing up and coming down a grade, right. So, that is a notation that you will see. So, now we are going to make an approximation. Okay. Let us assume that the grade angle is small enough such that cos theta s is almost equal to 1, that is one assumption, and we will also assume that the values of HA, HT are almost equal to H. Okay. So, these are two assumptions that we are going to make, okay, just to simplify these expressions. Okay. So, let us make these two assumptions. Okay. So, this is one assumption and this is the second assumption. Okay. So, once we make these assumptions, immediately we can observe that W F, what will happen to WF? It will be 1 by L, let me rewrite in this form, I can rewrite it as WL2 by L, because cos theta s almost becomes 1, and then we pull H common, because HA, HT and all are approximated as H. So, we take H by L common and this becomes W by G A H plus RA plus RD plus W sin theta is. Correct? I am sure all can agree with me, right. So, what happened? Cos theta is we are taking as 1, HA and HT you are taking as H. So, it gets simplified in this manner. So, similarly WR will become WL1 by L plus H by L W by G AH plus RA plus RD plus W sin theta is. Okay. So,
WA by G, H should
W okay. So, yeah, sorry, no, H is not there, sorry, in both the equations. Thanks, yeah. So, this is yeah, we have taken H outside, right. So, H is no longer there, thanks, yeah. So, we get this equation. Now, we can immediately see that the term within the square parenthesis in both these equations we get from equation A, right. So, if you go to equation A, W by G A plus RA plus RD plus the grade resistance Rg will be essentially equal to F minus RR, right. So, how do I get this? From equation A, right. If you go to equation A, if you take RR to the other side, whatever is remaining on the right hand side is what we find in the square bracket. So, this becomes F minus RR, okay. So, this also becomes F minus RR, right. So, consequently the expressions for the normal load become WF is equal to WL2 by L minus H by L F minus RR, and the normal load on the rear WR becomes WL1 by L plus H by L times F minus RR. So, this is how the normal loads on the front and the rear simplify to. Okay. So, in the next class what we are going to do is that like we are going to physically interpret these equations and work with them further, and ultimately what we are going to figure out is to when we shall consider a front wheel drive and a rear wheel drive, and then like how do we match the vehicle performance requirements with that of the powertrain to determine the first cut values of the gear ratios. So, that is the analysis which we will follow up in the next class. So, I will stop here for today. Thank you.